All right. One thing I prefer to do when writing a game engine structure is creating my own game math library. Because a lot of the time, even though Raylib or SFML or SDL with its, I think there's like some type of extra math thing you can include there. They come with their own stuff. Unity, Godot, Unreal Engine, they have that stuff. I like to write it from scratch. It kind of helps me really remember, practice, and use the code that I'm writing for that purpose. And that's what we're going to do. We're gonna build a slight math library to go with this game engine. Now remember, we're building Pong. Why do we need all this stuff? The fact of the matter is, you can build Pong. You can build Pac-Man. You can build who cares what. The point is, can you build it in such a scalable way that your program can build other programs without rewriting the whole code base? That's the goal. So, without further ado, let's move on to the math library. All right, from where we left off, guys, we made the loop, the globals here, and I talked about how I generated this makefile using a large language model. And yeah, so file, new file, and I'm going to call this mathlib.header. Here, I am not going to use a class. This is something that needs to be said. Not every time you make something do you need an object to represent it. There is different tools in a programmer's toolbox, and today we're just going to use inline functions. Now, there's a few things that we need to do. So the end goal here, so the goal is to be able to represent vectors, as in I want to get the distance between two spots. I want to be able to find the magnitude. I want to be able to normalize these things, so on and so forth. So I'm going to make an inline, and I'm going to start with void. The return type will change here. And I'm going to say, hey, distance, because this is what I want to calculate. And then again, an inline void magnitude, an inline void, and I'm going to call this length here, inline void normalize, and inline void angle. Now we could preference this stuff with the word get. I think that's pretty representative. Now I know getting the length, that's going to return a float. Similarly with getting the magnitude, but getting the distance, oh yeah, getting angle as well would be a float. But getting the distance and the normalization, this is actually going to return a vector 2. Now, Raylib here, they actually provide, so if we hash include our globals here, they actually provide a vector. So notice we have vector 2, vector 3, vector 4. We want to use that stuff, but I'm not super familiar with Raylib, and I don't necessarily want to destroy any of their definitions. For example, if I made a struct called transform here, and I said, hey, my struct, it needs, a vector 2 called position, a vector 2 called size, so on and so forth. And then I'm like, yo, hey, transform, blah, blah, blah. Well, one thing that I do know about Raylib is it does come with transform. And so if we were to do that, we would overwrite their transform definition. Now, to prevent something like that, I think I've seen something like using std, blah, blah, blah. Let's say, for example, And by the way, never do this. This is a do not do example. I've noticed people doing, something of the sort here. Because if you use this namespace, then you don't have to sit here and type out, blah, blah, blah. You definitely never want to use something like that. The reason I bring it up is we're going to be creating our own namespace. This is going to keep our code independent, separated, and from redefining any other spot that may be inside of Raylib here. And I'm also going to pragma once here. This is going to be our safety catch from this being redefined multiple times in our binary. But, later we can call this dinzai and then call these functions. And notice this isn't a class. We don't have to instantiate it, and that's kind of nice. This object, that's the point, it's not an object. But we can still use some of these Raylib things and also potentially redefine some of this stuff as well. What do I mean by getting the distance between something? Well, we want the distance between one thing and the other. We don't need a reference here. Passing by value is fine. You definitely don't need a reference. You don't need a memory address. Passing by value, perfectly reasonable here. And same for this. So I'm going to do similar here. And then same for the angle. Now for length, you only need one. So a vector 2, and I'm just going to call this a vec. And same with this. The reason being is there's a slight difference between normalizing a single vector, finding the length of a single vector, and finding the magnitude of two different vectors. That might sound weird. So let's, as my college professor may do, let's draw it out, guys. All right, we're back here in A-Sprite. Let's jump on in. Let's throw in a color here. And let's start drawing. So let's say we have a triangle, right? So what are we talking about? Well, an entity, he may have a point in space. This is your player. And you might have an enemy right there, right? The distance between these guys is a distance between, and we're going to do a nice little red coordinate line here. Forgive me for it is slightly angled. Try to ignore that. Anyway, so there's a distance in the x for these guys, and there's a distance in the y. So yeah, just don't mind. It's slightly off. I'm hoping you guys are understanding the gist of this, though. In fact, I think you guys do. So this here, this green spot that I'm drawing, this green on the bottom, this is their difference in their x, this is their difference in the y. This is the magnitude. The magnitude, the distance between the two guys. And you can use this for a few things. So let's say this is our player, and as you can see the lovely mouse, and if I wanted to shoot bullets here in this trajectory, I could simply calculate the distance or the magnitude between the mouse and the player, and then use some angle math and, shoot the ball. This is one reason why I want to write a math library to handle this stuff for us, because it's going to have multiple use cases. This instance of get distance is more of a helper function for our magnitude. So what I mean by that is I want to return a vector 2, and inside this vector 2, we're going to say, hey, left-hand side, I want you to subtract from the right-hand side of this equation, and similar left-hand side of the y minus the right-hand side of the y. That way, here, we could say, hey, we're given these two values, and we're going to get a vector 2. I'm going to call it dist. This is going to equal our get distance. And I'm going to pass in our left-hand side and our right-hand side. So this gets us our distance here. Now, back over to A sprite. If you have taken algebra, we know that a squared plus b squared is c squared. And so if we have, what we calculated here was our change in x and our change in y, our dx and our dy. We saved that in a vector 2, and this function did the math, and it gave this function that answer, that distance here. So our dist.x, this would be our change in x. And then similarly, our dy would be our dist.y. And you could go from here and say, oh, so our dx times dx plus our dy times dy, this is our c squared. So if we took the square root of that function, this would be our c. Now square root is going to be a little squiggly there because we have to include C++'s math library here, like so. And then you would sit here and you would return C. But this was just to explain what's going on. The main reason I don't want to write it like this is, notice this is nice. This is concise. Can we do it in one line here? Absolutely. So let's go ahead and return. We're going to be returning a float. But I know inside that float, we're going to be needing our dx, which again is our dist.x. And we're going to be needing our dist.y. So this is our distance here. This is our c squared. And we just need to take the root of that. And so this is our magnitude. Similarly, getting the angle. Well, okay, back in math class, guys. So let's come up here. Let's get a different color. And I'm actually going to use a different color here, like so. All right. So let's say, we want to find, didn't know I could scroll on that part. You learn something new every day. Let's say we wanted to find this angle. Say this is where our player sits, this is where our mouse is. We wanted to shoot that bullet in this trajectory towards boop, 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 like so. We need to find this angle. So we know this is our dy, this is our dx between the 2 points. This angle here would use one of our trigonometric functions. So there's a nice little phrase I learned in high school, SOHCAHTOA. This is sine is the opposite over hypotenuse. So dy over our magnitude would give us this angle. Adjacent over hypotenuse would also give us this angle, or opposite over adjacent. Now we know how to calculate the magnitude, so we could use any of these. In fact, you could very arguably, you pass these in, grab that magnitude there, and use one of our sides and calculate that, but I prefer to use opposite over adjacent. So what I do And we'll come over here. I like to call this get distance function. And we'll do the same thing. So float dist is get our distance function, pass in left hand side and our right hand side. And we know we have a change in x and a change in y. Oh, my bad, this is a vector 2. It is not a float. But we know we have our change in our x and our change in y here. Now, the tangent function returns when we do our opposite over adjacent. This returns, I think, an angle. I could be wrong. It very well could be, and I don't want to lead you down the wrong path here. So tangent math, what does it do? Now this is yeah. So tangent of the angle is opposite over adjacent. So that's the key point. What I'm saying here is the tangent of our theta is our opposite point over adjacent. The reason I bring this up is we want our angle. We don't want the tangent of our angle. We want straight up our angle. And there's a thing called an arctangent. That's basically just like having a tangent to the -1. The arctangent. I bring this up because here I want to call the arctangent. So A tan 2. And there's two arctangents here. There's the arctangent and there's the arctangent 2. We're going to use the A tan 2 function here, and I'm going to pass in the dis.x, or no, the dis.y and the dis.x. So y goes first in this case, opposite over adjacent, and we're going to return this float. This gives us the angle between 2 points. So this could be the angle between the mouse and the player. This could be the angle between the player and a wall or any other entity. And moving along, getting our length. So grabbing the length of a vector. Well, it's basically the magnitude, except we don't have a dx and a dy. So what I'm going to do is I'm going to return, and in here, go like this, and we know we're going to take the square root of what's going on here, and this is just itself. So multiplying its own x and its own y's together. This is the vector length. Why do we want that? Well, there's a few scenarios here. So let's say you have a player, and he can move up, he can move down, he can move left and right. But you said he could move diagonal too. Now, this is where things get kind of funny. He could end up moving a little bit faster going diagonal than left, right, up, or down. And I'll showcase this, but using a kind of this little system of normalization, we can prevent that. And what we would do for normalizing is we would get the length. So I'm going to say, hey, I'm going to call this get the length function. We're going to pass in our vector. And then I'm going to say, hey, vector, I want you to divide by the length. And I'm going to do that for the x and the y. I did put a comma there on purpose. And we're going to surround that in curly brackets. I'm going to put vector 2 around it. And then I'm going to return. And use a semicolon at the end. This is constructing that vector 2. But taking the x divided by the length and the y divided by the length, this normalizes our vector. It keeps it between 0 and 1. So let's say, you're moving up, which would be -1, and you're moving to the left, that would be -1. In those trajectories, without normalizing, both that 1 and -1 are both going to be used, and, stuff's going to happen.